Today we'll discuss about the series LRC circuit, which is a part of the syllabus for semester 2 physics honors. So the topic is series LCR circuit connected with obviously AC source. So we'll start with it. So just draw a diagram. This is resistance R in series, connected in series with inductance coil L, okay, and which is in turn is connected with the capacitor C, and it is connected with an AC source, say V as a function of T. Okay, so this will be the voltage about this is given by V subscript R. We'll take small v for AC component. Here it's V subscript L, and here it's V subscript C, and the current over here is I as a function of T. So this is the circuit which we'll discuss over here. Here we'll consider a voltage V subscript T applied to a circuit, okay, and at any time I subscript is the instantaneous current across, and as the voltage across R, L and C are given by V subscript R, small v subscript R is equal to I into R, small v subscript L is equal to L di by dt, and V subscript C will be equal to Q by C. That's it. So applying the KVL, Kirchhoff's voltage law, okay, or EMF equation for the circuit, will have V subscript R into as a function of T, V subscript L as a function of T, V subscript C, okay, as a function of T is equal to V subscript T, or V as a function of T rather. So this was the Kirchhoff's voltage law, okay, and then we'll write, this could be written as I into R plus L di by dt plus Q by C, okay, is equal to, in the place of V as a function of T, we will write V naught E to the power j omega t. So this will be equation number 1. Here V subscript T, this is the sinusoidal wave function, or the voltage. Now this equation 1, it will be differentiated with respect to time to get L d square I by dt square plus R di by dt plus dq by dt, that will be I, so I by C is equal to j omega V naught e to the power j omega t. So this will be your equation number 2. Now further, the steady state solution for the current in this particular case will be given by I is equal to A E into j to the power omega t, where A, here A is a complex quantity. Okay, now substituting this particular solution in equation number 2, we'll substitute this value over here to get minus omega square L plus j omega R plus 1 by C into A is equal to j omega V naught. Now we'll see over here, we'll just divide this particular equation by j omega on both the side to get V naught, and the left hand side will have A into R plus j omega L plus 1 by j omega C. Okay, so this is what you will get, and this will be your equation number 3. Now solving equation, okay, this equation 3 for A, we'll substitute this here to get I equal to V naught by R plus j omega L minus 1 by omega C. We'll take out j as a common factor over here into e to the power j omega t. So this will be your equation number 4. Now moving ahead, now here what we can say, this will be your impedance. Okay, so that will be Z equal to R plus J omega L minus 1 by omega C. Okay, so this is the value Z. Now this could be again written as Z, mod of Z will be given by under root R. So this will be for this, we'll write here equation number 5, and then we will move ahead. Write Z is equal to R square plus omega L minus 1 by omega C whole square. So this will be equation number 6. And obviously from the previous equation number 5, we'll have tan theta equal to omega L minus 1 by omega C by R. This could be written as X by R. So this will be equation number 7. Now the quantity X equal to omega L minus 1 by omega C. This is termed as reactance. Okay. Now again using equation number 5. Okay. We can using equation number 5 we can rewrite equation number 4. This equation, actually this equation number 5, using equation 5 equation 4 can be written as I equal to V naught by mod of Z into E to the power J omega T minus theta. Okay, so this will be your equation number 8. Now we know that V as a function of T could be written as V naught cos omega T. The physical solution for the current is obtained by taking the real part of the equation 8. Okay, so if we take the real part of equation number 8, we can represent the physical solution of, if on the other hand Vt is equal to V naught sin omega T, the corresponding physical solution is given by the imaginary part of equation number 8. So in this particular case, the current is obtained by taking the real part, and in this case the corresponding physical solutions are obtained by taking the imaginary part. Imaginary part of what? Imaginary part of equation number 8. Equation number 8. Real part equation number 8, imaginary part equation number 8. Here all the here now putting I naught, rather I naught is equal to V naught by mod of Z, and using RMS value. You know what is RMS value, already we have discussed. So mod of I will be equal to I naught by root 2, and V is equal to V naught by root 2. So we'll get equation number, obviously equation number 8, we'll get mod of I e to the power minus j theta is equal to mod of V e to the power j theta by mod of Z e to the power again j theta, or V is equal to Z into I. So this will be equation number 9. Now here all the quantities are in phasors. Now equation, this could be, equation number 9, it is the general form of Ohm's law, if you could remember. This is the general form of Ohm's law. Now the phasor diagram can be drawn for the following cases. We will say like this, that if omega L is greater than 1 by omega C. Now what we can say, this is case 1, and in this particular case here you can see that the reactance, inductive reactance is greater than the capacitive reactance, since tan theta is given by what we have discussed in the case equation number 7 rather. Okay, so that will be positive. Okay, so in this particular case we can say like this, if this is Ri, and if you will minus j 1 by omega minus j 1 by omega c, and here we have j omega Li. If this is more than this, as we have considered over here, so we will have j omega L minus 1 by omega c. Okay, so obviously with I, here it's I, so I, so the resultant will be given by Zi, and this will be your theta. So this was the first case, okay, where we have considered omega L greater than omega 1 by omega c. Likewise, we can consider a case where omega L is greater than omega L is less than 1 by omega c. This is case 2, less than omega c, case 2. Now in this case the capacitive reactance predominates over the inductive reactance. Okay, so here the angle theta is negative. So in this particular case, this Ri, it's, and here we'll have j omega L I, and the resultant will be along this direction, so that will be given by j omega L minus 1 by omega c into I. You can show it here, minus j by omega c into I. So the resultant will be given by this. So zi, and this is the angle theta. So the value, it's the theta is along the negative direction. Similarly, case 3 we can just consider that omega L is equal to 1 by omega c. Now here the total reactance is 0. Total reactance is 0. So the circuit is purely resistive. And the angle theta will be 0, so that the current and the applied voltage are in phase. So the phasor diagram in this particular case will be like Ri. Here we have j omega Li and minus I by omega c. So this will be the phasor diagram for this particular case 3, when omega L is equal to 1 by omega c. Related to the other topic associated with series LRC circuit, we'll consider in the next lecture. Until then, thank you very much.